This term project explores the impact of visual programming languages, or VPLs, and visual programming environments, or VPEs, on science, technology, engineering, and math education and learning, also known as STEM. This topic is important and relevant to cognitive science as it explores our computational representational understanding of mind, specifically around how we share knowledge and learn from each other. Furthermore, learning the basics of computer programming is becoming a necessary skill in both academic and professional contexts. Even so, computer programming is often seen as an arcane art full of esoteric symbols, rites, and incantations. The typical image of a programmer is of a person wearing glasses bent over multiple screens full of indiscernible symbols written in an alien and otherworldly script. Our programming no longer requires an advanced education, fluency in English language, or even familiarity with a traditional high-level textual programming language, or TPL, such as Python, Java, or C++. One salient example is Scratch, an open-source visual programming language targeted toward educating children how to program using an intuitive drag-and-drop interface. Scratch has been so effective, it now empowers kids in 196 countries to learn to develop applications in over 70 spoken languages with an impressive 45% female user base. Let's now go deeper into the design, results, and conclusion of the research project. For this term project, I chose the literature review track and covered 12 research papers on visual programming and education in STEM-related fields. The review was conducted over the course of 100 project hours spread across 4 milestones. Papers were selected in the fields of grade school education, undergraduate education, and professional training settings, such as computer-aided design and cybersecurity. Throughout the review, the focus was on exploring the following research questions below. Research questions. What is the state of the art of VPLs in comparison to traditional text-based programming languages? Do VPLs help students learn basic computer programming concepts such as working with inputs, outputs, loops, conditional branches, and switches? Can VPLs help individuals learn more advanced concepts such as data structures and algorithms? Are there trade-offs between learning to program graphically rather than textually? Research results are best summarized by the graph adapted from Ashish and Hannah's paper on comparative evaluation of parametric design published in the interdisciplinary journal of Design Studies in 2017. The graph shows how in VPLs, learning represented as L takes off at an accelerated rate with respect to time, T. Researchers argue this is due to beginners not needing to invest time learning the grammar, syntax, and mechanics of their respective programming language, such as how to compile and link C++ code, or how everything is a class in Java. This allows students to focus on learning the basics like working with inputs, creating variables, following sequences, loops, and conditionals without having to worry about the details of TPL syntax. Furthermore, research found that the rapid results yield a positive emotional response, lower stress due to syntax errors like forgotten semicolons, lower the cognitive load on students, and reinforce the learner's computational self-efficacy, or an individual's confidence in their ability to perform a task. Inversely for TPLs, they require a huge upfront investment from the students and teachers, causing stress and anxiety in some, and increasing the likelihood of hurting an individual's computational self-efficacy. However, once students have mastered the mechanics of a traditional TPL language, they can quickly close the gap with VPLs and even surpass their peers in terms of velocity of delivery, program size, and complexity. So what does this mean? Are VPLs just for kids, or do we go all in on TPLs as the optimal teaching tools? Let's look at the research questions. In the current state of the art, VPLs are geared toward application-specific use cases such as education and AutoCAD. This contrasts with TPLs, which are geared toward general-purpose use cases. In fact, even Scratch VPL was written in the traditional JavaScript TPL. VPLs lower the barrier to entry and allow for the introduction of propositional logic concepts, such as sequences and loops. Furthermore, VPL's iconic representation allows for students to spend more time building and validating mental models than learning syntax, resulting in positive emotions, reduced cognitive load, and improved self-efficacy. As the complexity increases, Ashish's graph shows VPL's usefulness as an educational tool tapers off, and the need for TPLs becomes noticeable. In fact, students have been observed grouping larger blocks or chunking for reuse, and this is why most VPLs allow for the execution of TPL within custom VPL blocks for more advanced users. Alalema et al. Refer to this technique as scaffolding and suggest a better point of view is VPLs plus TPLs. Research findings suggest VPLs are effective at building interest, while TPLs are effective in more complex scenarios such as algorithms and data structures. VPLs lower stress but have limitations, while TPLs increase stress but offer students near limitless creative potential if they make it through the program. Based on these findings, I conclude that when used correctly, both visual programming languages and text programming languages are effective tools in STEM education and offer a window into human cognition when teaching, learning, and applying computer science concepts.